Hey everybody, welcome back to another business calculus video. Sorry about the rain audio. It's obviously raining today, but either the video gets recorded today or it's not ready in time for class, and I figured that the former would be better than the latter. So, in this video, we are going to be finishing off our section on optimization. So, again, optimization, right? The idea is you want to find the absolute maximum or minimum of some function, and we're going to apply that to real-world situations. So, let's outline a general procedure for solving real-world optimization problems. The first step, as always, whenever you're working with a real-world situation, is to translate it into math world. So, assign your variables properly. And draw any helpful pictures. Alright? After that, okay, we've assigned our variables, we've gotten all our kind of set up in terms of naming things. Now we're going to start relating the variables one to another so we actually have a function to optimize. So, step 2, find an expression for your quantity that you're trying to optimize. In terms of the other available variables. Alright, so you might find one expression, you might find multiple. Typically you'll only need one or two of them, but as many as it takes, right? Just relate the variables however you can. And then next, what you can do is use the conditions that are given to you to rewrite the expression from 2 in terms of one variable. And now that we have a function in terms of one variable, we can apply all of the optimization techniques that we have talked about so far. Oh, and something that might be helpful when doing this, make sure to consider physical constraints. For instance, if you're trying to talk about like the side length of a box, you wouldn't want your box to have negative side length or 0 side length, right? Because that's kind of an issue, having a flat box. Okay, and then step 4, optimize. Using any of the methods that we have talked about thus far. So this is our general procedure, and we've already kind of discussed all of the theory because this 4th step is really the math content. How do you actually do the optimization? So let's do some examples to see, okay, how do you get this all set up properly and then actually do the optimization? those erasers get so chopped up even after just one thing. All right, example. It's annoying enough. Jacket is too small. All right, let's find the dimensions of a rectangle of area 144 feet squared with the smallest possible perimeter. So let's talk about kind of the setup for this question. The idea is, hey, there's a bunch of rectangles out there that have an area of 144 feet squared. For instance, you could do a rectangle that's 10 feet by 14.4 feet. You could do a 12 by 12, right? So that'd be a square. And the question is, okay, what dimensions of rectangle actually give you the smallest possible perimeter? Maybe you're trying to enclose an area with a fence, right? And you want to spend the least amount of money on materials as possible. So these are kind of useful questions. Well, let's think about how we solve this problem. If we draw our picture, we have a rectangle. Let's call the sides of the rectangle X and Y for the sake of it. And we know they're enclosing an area A equal to 144 feet squared. All right, so let's figure out what to do. We need our perimeter in terms of our variables. So our perimeter, P, standard definition of perimeter for rectangle, it's going to be the addition of all of those sides. These two sides are the same, these two sides are the same. It's a rectangle. So the perimeter is 2x plus 2y. Now let's get the area in terms of our variables. The area will be equal to x times y. All right, so we're trying to optimize perimeter, specifically trying to minimize perimeter, and we can use this relationship here to do it. Our given constraint is that the area is 144 feet squared. We'll drop the units as we work through the problem. So we know that 144 is equal to x times y. Solving for y in terms of x, that gets us 144 over x is equal to y. Okay, why go and do that? Because it allows us to, again, step 3, rewrite this expression here, which is in terms of two variables, as just a function of one variable. Let's plug our definition for y into this equation. Then we get that p is equal to 2x plus 2 times 144 is 288 over x. Great, that's a function of x. So let's even write it as p of x. And we can optimize that function. So let's do so. Let's also recognize some constraints on our variable, right? Since when we optimize, we need to do it on a closed interval, otherwise things might not work out properly. Let's recognize here, x has to be greater than or equal to 0, right? Wouldn't make sense to have a negative side length. And also, x has to be less than or equal to 144. Right? Because otherwise, you'd end up with, or I guess, sorry, not less than or equal to 144. Just less than infinity, I guess. you can make it work with bigger than 144. That's on me. Okay, so 0 is less than or equal to x, less than k. We don't have a compact domain, we don't have a closed interval, but we can still use our standard optimization techniques to make this work. Alright, here's how. We'll take our derivative with respect to x. P prime of x, okay, this is 2x plus 288 x to the negative first. So our derivative will be 2 minus 288 over x squared. To find points in the domain where this, to find points that are candidates for optimization, we say, okay, where does this derivative not exist or equal to 0? Okay, well, p prime of x does not exist at x equals 0. So that's one possible point of optimization. But we can rule this one out right off the bat. Because if x is 0, then you have a 0 length times the side, right? And that gives it a rectangle with 0 area. But we know the area is 144 feet, which is not 0. So we can automatically rule out this x equals 0 case. Now let's solve for when p prime of x equals 0. So 0 is equal to 2 minus 288 over x squared. Multiplying everything through by x squared gives you 0 is equal to 2x squared minus 288. So 288 equals 2x squared divided by 2. 144 equals x squared, which means that plus or minus 12 equals x. But based off the physical conditions we already mentioned, it doesn't make sense to have a negative side length. That tells us x must be positive 12. Alright, so that's our x value. And it's the only thing that remains, right? This is the only possibility for our optimization. Now we need our other dimension, y. Thankfully, we have an equation relating x and y right here. So y is equal to 144 divided by 12, which is coincidentally, again, 12. So our dimensions are x equals y equals 12 feet. How about that? The smallest perimeter rectangle enclosing an area is going to be the square that has that area. So that's neat. Let's do another example. All right. Suppose a store manager wants to fence off an area. Let's say it's an 8,000 feet squared display area. With one side being a store wall, and we'll assume that the store itself is physically big enough that whatever dimensions we use for our fence, the store wall can actually act as one of those four walls. So one side is the external wall of the store. Two sides are made of pine boards which costs $6 per running foot. And the last side will be made of galvanized steel. Costing $3 per running foot. Okay, so we have this up. Our goal is going to be to figure out what dimensions should we put on our two sides of pine board and our one side of galvanized steel, that we can still enclose this area, but it'll cost the least. So let's minimize the cost of this project. And again, very helpful to draw a picture, so let's get that going. Okay, maybe we have our store wall over here. And then alongside that, we'll have our fence, or our display area. So let's label these two sides X, and this one Y. Right? It's a rectangle. So why that? Well, let's say that these two sides are going to be our sides made out of pine board. And this side over here is our galvanized steel side. You grab some. It's just this way. Okay, so we need to figure out values for X and Y that minimize how much constructing this thing will cost, while still making sure that we enclose an area A of 8,000 feet squared. How do we do? Well, let's get an equation talking about the cost in terms of our variables. The cost C of making this enclosure will be, okay, well, it's the cost of making each side added together. We have two sides that are the same, so how much does it cost to make side X? Well, if X is measured in feet, pine board costs $6 per running foot. So C will be 2 times 6 times X, right? So that's the cost of that one side, and there's 2 of those sides. So 2 times 6 times X, plus our steel side costs $3 per running foot, and we only have one steel side. So we have plus 3y. In other words, 12x plus 3y. Alright? What other information do we have? Well, we know that, oh, I'm sorry, I've been saying 8,000. Let's make it 800. For the sake of our computations, having nice numbers. No other real reason, but same idea. Okay, so our area is 800 feet squared, which means, well, how do we relate area to our variables? Basically, how can we get one of these variables in terms of another? Well, we know that 800 is equal to x times y. Our area is equal to the product of our two sides, which means that y is equal to 800 over x. So we can rewrite our cost as being a function of x equal to 12x plus 3 times 800 is 2400 divided by x. Alright, and again, we're optimizing on 0 to infinity for x. So let's talk about how we're going to do this problem, and then let's talk about the technicality for this problem. Technicality said, how we're going to do the problem is we're going to take the derivative, set it equals 0, and solve. Technically, though, that process only works on a closed interval a to b. Right? So you could optimize between here and here, say. Right? But our value for x can be anything as long as it's not 0. And as long as it's positive. So we really are trying to optimize on 0 to infinity. So how do we do that? Technically, our procedure won't work. The only real procedure that would work for this would be to try to sketch c of x and find a local minimum that way. Right, so if you graph c of x, it would look something like this. But here's the crazy thing. Looking at this graph, we see that past the minimum, the single minimum that we can show it'll have, there is no other local minimum. This graph will keep going up forever and ever. You could do some analysis on that by saying, oh, I'm going to take the first derivative and I'm going to solve for when it's positive, and I'm going to see it's going to be increasing forever after a certain point, which means that we can use our optimization techniques maybe on like this closed interval right here, and we know that we'll actually get our valid answer. So that's the technicality behind what we're doing. In practice, we're going to take the derivative, set it equal to 0, and that'll give us our desired results. Right? It's worth mentioning, hey, that's what's going on behind the scenes. We're not really optimizing on a closed interval, so there's no endpoints to check. Okay. So, c of x is equal to 12x plus 2400 over x. Taking derivative, that gives us c prime of x is equal to 12 minus 2400 over x squared. Okay? Doesn't exist at x equals 0, but we don't care about the x equals 0 case. Let's set it equal to 0 and solve. So 0 is equal to 12 minus 2400 over x squared. Multiplying through by x squared gives 0 is equal to 12x squared minus 2400. 2400 equals 12x squared. Dividing both sides by 12 gives you 200, I believe. Equals x squared. Yes, 200. And now we take a square root on both sides. And we get that plus or minus 10 times the square root of 2 of x. Again, we need the side length of a fence to be a positive number, so we take it. Positive number. So that's our dimension for x. Is positive 10 square root of 2. Make sure those lines don't blend together. And now we need to solve for y. Okay, well, y is 800 divided by x. That'll be 80 divided by the square root of 2, which if you like me, having your radicals on the top, that'll end up being 40 times the square root of 2. So those are our dimensions. X is 10 times the square root of 2, and y is 40 times the square root of 2. And you could ask, okay, so how much does this project actually cost? Well, then the cost will be 12x plus 3y. So 120 square root of x plus another, square root of 2, plus another, 3 times 40 is actually 120 as well. So our total cost would be 240 times the square root of $2. How about that? Nice extra for us. Let's do another example. More complicated one. This side. Sorry, rain is throwing me off, I feel. Okay, let's do perhaps another very real world oriented one. Say we have a book designer. Right? Who reads books anymore? So maybe this isn't quite as real world as I thought. A book designer has decided that the pages of a book should have 3/4 inch margins at the top and bottom, and 1/4 inch margins at the sides. Okay, so that's the pages of the book, which essentially say, okay, where's the printed area? Well, the printed area is going to have this margin on the top and bottom and this margin on the sides. But furthermore, each page, so the overall page, printed and non-printed area, should have a total area of 60 inches squared. Our goal is going to be to determine the dimensions of the page that will give us the most printed area on the page, right? You want to print as few pages as possible to minimize cost, so you want to figure out how to get as many words on there given these constraints. So, determine page dimensions that maximize printed area and then let's actually find out how much printed area will we get. So what are the area and dimensions of the printed area? So first we maximize printed area based off page dimensions, and then we're going to compute some stuff about the actual printed area. And if that's confusing, don't worry. That's what pictures are for. Alright, so our picture for this situation is going to be a couple of rectangles sitting inside of each other. So we have the big rectangle, the overall page of the book, and then the small rectangle is the printed area inside of the page. We're told, okay, 3/4 inch margins at the top and bottom. So using classic engineering notation, we'll put 2 arrows there and 3/4 inches. And over here on the sides, we have 1/4 inch margins. Alright? And we're trying to maximize based off the dimensions of the overall paper. So let's say that X is the width of our page and Y is its length. You could also use, heck, let's even do it. Get away from using X and Y. Let's use L and W. Why not? Alright, so what do we know so far? Let's just start writing down all the relationships between variables that we can possibly find and hope that something good comes out. We know that area that is printed, aka the thing we're trying to maximize, is what? What are the dimensions of it going to be? Well, it's this dimension times this dimension. What are each of those dimensions? Well, the width of the overall page, we're going to subtract 1/4 inch on each side, and that'll be the width of our printed area. So it's going to be W minus 2 times 1/4, W minus 1/2. Similarly, to find the length of the printed area, we're going to say, okay, it's the length of the overall page minus 3/4 of an inch there, minus another 3/4 of an inch there, so minus 3/2 inches overall. So that's our printed area. W minus 1/2 times L minus 3/2. Okay? I still need a way to relate L and W all together. How about the area of the page as a whole? The area of the overall page is the width times the length. Standard formula for an area of a rectangle. But we're also told, hey, total area of 60 inches squared. So, we know that a page has to be equal to 60. Now that we have these two relationships, we can solve for one variable in terms of the other and get optimizing. So from here, let's say that 60 divided by L is equal to W. So width is 60 divided by the length of the page. Do I have more space? Yeah, let's use this space. Let's get optimizing. We now know that the area printed as a function of the length is going to be just what happens when we substitute in this definition for W. So it'll be 60 divided by L minus 1/2 times L minus 3/2. faced with a choice. Depending on user preference, you could choose to distribute this out and then differentiate, or you could use the product rule. Let's do the product rule for the sake of it. You get that the printed area, or rather the derivative of the printed area, so A printed L prime is equal to, okay, first times derivative of the second. So derivative with respect to L of L minus 3/2 plus second times the derivative of the first. Okay? Well, this is going to have derivative 1 by the sum rule. So this is just 60 over L minus 1/2, all times 1, so not even worth writing, plus L minus 3/2 times, okay, that's going to go to 0. That derivative by the power rule, or the quotient rule, take your pick, will be negative 60 over L squared. I guess we didn't get to escape distributing out in the end. We're left with 60 over L minus 1/2. This will give us minus 60 over L plus 3/2 times 60 is 108 divided by 2, 90 over L squared. Those cancel out. We're left with 90 over L squared minus 1/2. Great, now we can optimize. Set this thing equal to 0. Multiplying through by L squared gives us 0 is equal to 90 minus 1/2 L squared. Make sure you have that down, then we can erase. Cool, I'll leave the picture up. Because I think it's helpful. Alright, 0 is equal to 90 minus 1/2 L squared. That means 1/2 L squared is equal to 90. L squared equals 180. L is equal to plus or minus square root of 180, which is 9 times 20. So we'd have 3 times the square root of 20, which will be 6 times the square root of 5. Alright, and obviously we're working with a length, so we're going to choose the positive version. So that's your length. 6 times the square root of 5 inches. And our width, I erased it, but we had that relationship saying, hey, it's 60 divided by L. We solved for that earlier. So you'd end up with 10 divided by the square root of 5, which is, let's see here, 10 square root of 5 divided by 5, 2 times square root of 5 inches. So that's our length, and that's our width. Done. Well, with the first part of the question. These are the dimensions that will maximize how much printed area we get. Now the question is, okay, well, what is the actual dimensions and area of the printed page? Well, the area that's printed was equal to W minus 1/2 times L minus 3/2 equals, okay, so you plug in L here, or L there, you plug in W there, and you get something. I feel lazy today, so let's call that an exercise, is plugging this in here and that in there and doing the arithmetic. And then as for the actual dimensions of the printed page, the printed width is W minus 1/2. So you'd end up with 2 square root of 5 minus 1/2 inches. And then the printed length will similarly be 6 times square root of 5 minus 3/2 inches. How about that? So it turns out that the printed width is actually 1/3 the printed length. Ditto for the actual width of the length and the page. So that's cool. Yeah. Let's see, do I have any more examples written down? I do. Let's do one more. Alright, so a company makes stew cans with a desired capacity of 36 inches cubed. Let's find the radius and height of a design that minimizes the metal used. Right? Using the least amount of material possible so the product costs the least amount of money to make. How do we do this? Well, first we should figure out what is it that measures the metal used. The metal used is precisely the surface area of the, in this case, cylinder. Right? Because that's all the actual material that's going into making that boundary. Okay, so how do we solve this? Let's draw our pictures. So we have our cylinder there, that'd be the can all together. And then let's draw it just so we get a picture of its surface area. We have the circle on the top. We'd have this wall here, which if we were to take a slice and unfold it, would look like a rectangle. Then we have the bottom circle. So if we, this is again saying just unfold that can, this is what you would get. So how do we go from there to solving the problem? Well, let's start by labeling. We know that the whole thing has a volume of 36 inches cubed. We know that it's going to have a radius, let's call it R. So this is the same R as that. And it's going to have a height H. So this is the same height as that. You might say, okay, what's this other side of the rectangle? Well, let's remember, this rectangle wraps around the circle, so its length is going to be the same as the circumference of the circle, which, for those of you who remember your geometry, is 2 pi times the radius. Again, we have the same radius down there. Alright, so now we have diagrams that depict both the volume of the shape and its surface area. So we know that 36 is the volume, which will be pi r squared times h, right? Area of the circle times the height of the circle. That gives you the volume. Okay? And then we also know that the surface area, aka the amount of metal that's getting used, is, well, let's add the area of each of these chunks together. Each of these circles has area pi r squared. There's 2 of them, so we get 2 pi r squared. Then we also have the area of this rectangle. Length times width. We're going to add on an extra 2 pi r h. Alright, so from this first equation right here, this 36 equals pi r squared h, let's solve for one of our variables. I like h because it seems to just be kind of sitting over there by itself, so let's get h in terms of everything else. 36 divided by pi r squared is equal to our height. So, the metal we're using as a function of the radius is 2 pi r squared plus 2 pi r times 36 over pi r squared. The pi's cancel, and we're going to be left, and r cancels with one factor there, and we're left with 72 divided by r. Okay? So, let's optimize. M prime of r, take the derivative, will get you 4 pi r minus 72 over r squared. Alright, make sure you have everything over here down. We'll erase it soon. Alright, so that's m prime of r. Make sure that prime is visible. We set it equal to 0. Since we know that r has to be a number strictly greater than 0. So 0 equals 4 pi r minus 72 over r squared. Let's multiply everything through by r. We get 0 is equal to 4 pi r cubed minus 72. 72 equals 4 pi r cubed. 72 divided by 4 is equal to, let me think about that for just a second. 32 plus 8, so 18. Divided by pi is r cubed. So now r will just be the cube root of 18 divided by pi. So that's one of our dimensions. And now we also need the height, which is 36 over pi r squared. cube root of 18 over pi squared. So that's our height. If you wanted to do some simplification, that would be 36 divided by pi times the cube root of 18 squared divided by pi squared. 18 squared is 180, 260 plus 64. Yes. So 324. Let me check if that's a proper cube root. I'll do that off camera. Alright, so you do some of the math, and it simplifies to being 12 divided by pi times the cube root of 12 over pi squared. Turns out there's an extra factor of, this is 27 times 12, so if you pull out the 3 and then divides, which, if we wanted to get kind of poetic about it, that's 12 divided by, okay, we have a cube root of 12. Then we have pi to the negative 2/3 times pi. Which is pi to the 1/3. So we're going to be left with 12 to the negative, or sorry, 12 to the positive 2/3 times pi to the negative 1/3. Or if you wanted to rewrite that even further, you could do it as the cube root of 144 divided by pi. Cube root of that whole thing. Alright, so although the numbers got a little bit messy there at the end, hopefully the process was clear for this example. We got the volume in terms of our variables, put one in terms of the other. We put the thing that we want to solve for in terms of our variables, substituted it in, getting it all in terms of one variable. We optimized using our standard procedure of taking the derivative and setting it equal to 0, and then we just put all the numbers together. The numbers are kind of the least important part of the problem, at least with regards to the theory of it, maybe slightly more important when you're trying to actually build the can. Alright, so in general, that's our process for solving optimization problems. Put everything in terms of math world, draw any pictures that might be helpful, get relationships between the variables, derivative equals 0, optimize. Hopefully that was good for y'all. Again, sorry about the rain, and have a great rest of your day.